Okay, so today's lesson is going to be on mole ratios and the use of a Rebecca chart in order to use these mole ratios. So, when we have an equation, our reactants make our products, we can use a mole ratio to determine how much of a product is made from a specific amount of reactant, how much reactant is needed to get a specific amount of product. There's all different things we can do. It starts with a balanced equation. So when I start here and I look at my equation and I balance it, I have 2 moles of H2S plus 3 moles of O2 yields 2 moles of SO2 plus 2 moles of H2O. So 2.4 moles of sulfuric acid reacts with oxygen gas to form sulfur dioxide and water. Part A. How many moles of oxygen gas are needed to completely react with hydrosulfuric acid? So here's my hydrosulfuric acid, and I have 2.4 moles. Now, when I do my Rebecca chart, it is important to remember these go through the mole. So if you're given a mass, you have to first find the mole. All right, where do I start? I'm starting at my hydrosulfuric acid. There are 2 moles of hydrosulfuric acid, and we're going to put that over itself times my before. So my change is always my before and then my mole ratio. Where I start, I put it over itself. And the reason I do this is because whatever these values are, 2 divided by 2 in this case is a 1. So it's going to give me 0. This is a subtraction. So remember, reactants make products. So reactants are being used up. And we're going to make the assumption here that all of this reactant gets used up. So there's a 0. So that's why we start here and we put 2 over itself, because we want the change value to subtract from the 4 to give me 0. Now, how much oxygen gas is needed to completely react? All right, we're going to again make the assumption that all of this oxygen gets used up. So my after is going to be a 0. How much do I need? We're looking for the before in this case. If I have 2.4 moles of hydrosulfuric acid, if 2.4 moles of hydrosulfuric acid is on top, mole of H2S is going to go on the bottom. Remember, what is on top goes on bottom. And I'm looking for oxygen gas. So I'm going to go to the mole of oxygen gas, and I'm going to use my balanced equation. There are 3 moles of oxygen gas and 2 moles of my acid. So my mole ratio here is 3 over 2. So my change is 3 over 2. Now, this is multiplied by 2.4. So, times 2.4. Again, reactants are being used up. So there is a subtraction. So 3 times 2.4 divided by 2 is a value of 3.6. So this change, 3 over 2 times 2.4 is 3.6. 3.6 minus itself is 0. So I have 3.6 moles of oxygen gas that would be required. That is the bare minimum amount of oxygen needed. How many moles of sulfur dioxide would be produced? So we're now at the sulfur dioxide section. Now, when I have a reaction, before my reaction begins, I have only reactants. I have no products, meaning I have no sulfur dioxide and no water. And it's important to remember this is before. This is before the reaction starts. If there's no reaction, there's no products being made. All right, so here we go. If I started with 2.4 moles of H2S hydrosulfuric acid, if mole of hydrosulfuric acid is on top, it goes on bottom. And I'm being asked for sulfur dioxide, and this goes through the mole. And again, I'm going to use my balanced equation and the mole ratios. There are 2 moles of SO2 and 2 moles of acid. So what is my change? My mole ratio is 2/2. And I am multiplying this by 2.4. Now, products get made in a reaction. So this is an addition. So 2 divided by 2 is 1, times 2.4 gives me a value, a change of 2.4. 0 plus 2.4 is a value of 2.4. So how many moles of sulfur dioxide would I make? 2.4 moles of sulfur dioxide. Part C, how many moles of water? So here's my water. Again, I started with no water before the reaction. So if I have 2.4 moles of water, if mole of water is on top, it goes on bottom. I'm sorry. And this is not water. That's what I'm looking for. Oh my gosh, I just pulled a classic honors move. I have 2.4 moles of acid, H2S. So my acid is going to go on bottom. And what am I looking for? I'm looking for my water. So I'm going to go to the mole of water. Our Rebecca chart does go through the mole. And again, I'm going to use my balanced equation. There are 2 moles of water for every 2 moles of acid. So here's my ratio, 2/2 times my 2.4. And again, this is a product. I'm making products. So 0 plus this value is also 2.4. So I would also make 2.4 moles of water. So let's look at our Rebecca chart. What do we notice? We notice that the change is always being multiplied by what I was provided in the problem, in this case 2.4. We notice the bottom value on each one of these is a 2, because whenever I have whatever I start with, that always goes on the bottom. So every single one of my problems has moles of acid on the bottom. So that's where the bottom 2 comes from. The top number is the number that directly relates to what we are looking for. So 3 for oxygen, 2 for sulfur dioxide, 2 for water, and this 2 is 2 for H2S. Let's do another problem. Sodium reacts with 75 grams of oxygen gas to form sodium oxide. So step 1, we need to balance our equation out, and when we balance it out, there we go. Now, I told you the Rebecca chart goes through the mole. I was given mass. So my next step, I'm going to convert my grams of oxygen gas into moles, where 1 mole is the mass of oxygen from the periodic table, so that gives me a value of 2.34. So how many moles of oxygen do I start with? 2.34 moles. Now let's look at my part A. I want the mass of sodium needed to completely react with oxygen gas. So here I'm going from oxygen to sodium. Oxygen has a unit mole-wise of 1. So we're going to place that over itself, multiplying it by the 2.34. Now, reactants get used, so this is subtraction. So 2.34 minus itself gives me 0. We're making the assumption that oxygen is being used up completely. How do I get over to my change? We're going to make the assumption that sodium is going to be used up completely. In this case, is 0. There are 4 moles of sodium for every 1 mole of oxygen, 4 to 1, times my change value, 2.34. Now, since sodium is getting used up, it is a minus. All right, so 4 divided by 1 is 4, times 2.34 is 9.36. So 9.36 minus itself is 0. Now, it asks me for grams. This is in the mole. So my next step, I'm going to have to take my mole of sodium and convert it into the mass, where 1 mole of sodium equals the mass from the periodic table. So when we solve for that, we get 215 grams of sodium. How many grams of sodium oxide would be produced? So I'm looking here at my next section. So you'll notice we can start anywhere and we can go anywhere. So my next section is what I'm looking at. Now again, I have no product to begin with before the reaction starts. I have 2 moles of sodium oxide for every 4 moles of sodium, and I'm going to multiply by the same change value, 2.34, and so 2 divided by 4 times 2.34 is going to give me a value of 4.68, because 0 plus, we're making reactants, 4.68 is 4.68. Now, part B asked me for grams of sodium oxide, and that is the mole of sodium oxide. So my next step is going to be able to convert. I'm going to go from mole of sodium oxide to grams of sodium oxide using my conversion. 1 mole is the mass from the periodic table, which is 61.98 grams. So when we multiply these two values together, divide by 1, we get 290 grams of sodium oxide. Now, my problem, 75.0 grams, has 3 sig figs. So I have to put the 0 here and lock it in with the decimal to give me 3 sig figs. If the zeros confuse you, as always, when in doubt, you may scientific it out. If I have 3 significant figures, then I need 3 numbers in my scientific notation. So either one of these would be appropriate. Make sure you're taking into consideration your significant figures. All right, so what do we notice about part 2 versus number 1? Number 1, I was given hydrosulfuric acid. Number 2, I was given oxygen. You can start anywhere and go anywhere. All right, so these equations, we can start and go anywhere that we are provided. Let's do 2 more examples. Number 3, iron 2 oxide reacts with aluminum. So iron 2 oxide reacts with aluminum in a single replacement reaction to produce 2.5 moles of aluminum oxide. And iron is going to be off by itself. So in this case, what we've done is you've only been given the part of the reaction that you're being asked for, okay? But it should probably read 2.5 moles of aluminum oxide. That's what we measured, but iron is still present. So we could even add in and iron if we wanted to make it more clear. All right, so how many moles of iron are produced? So I was given 2.5 moles of aluminum oxide. So that is going to be my after. 2.5 moles is what was made. Remember, before a reaction starts, we have no product. So my before is 0. Now, in order to find my change, I must first balance my equation. So when I balance my equation, there we go. I have my balanced equation. And what do I start with? Aluminum oxide is what I was given in the problem. So that's where I start. So it is a 1 over itself times. 1 divided by 1 is 1 times what? Plus 0 to 2.5, that's going to be a 2.5. So 0 plus 2.5 gives me 2.5. So this after is my new change. How many moles of iron? So I have no iron to begin with before a reaction starts. You don't have any products. How many moles of iron? 3. Divided by 1 mole of aluminum oxide. And my change value stays the same. So 3 divided by 1 times 2.5 plus 0 is 7.5. So I had 7.5 moles of iron produced. How many moles of iron 2 oxide are needed? So this is where I started aluminum oxide, so I'm going to go from aluminum to my iron. Don't always go where you start to go to the next equation, all right? Always go from where you start. So I started at aluminum oxide. So my change, iron 2 oxide, I have 3 of them. And let me make this look a little more clear. It kind of looks like a, there we go. Over 1 aluminum oxide, and again, my change value is still 2.5. So we're going to make the assumption that iron 2 oxide gets used up to have none left. So this is a reactant, it's being used up, so that's a subtraction. So 3 divided by 1 times 2.5 is 7.5. So I have 7.5 moles of iron 2 oxide. Part C, how many moles of aluminum are needed? All right, so again, we're going to make the assumption that aluminum gets used up. All right, how do we know if it gets used up or not? That's a lesson for another day. Today's lesson, they all get used up. All right, I have 2 moles of aluminum and 3 moles of iron times the same change, 2.5. Again, reactants are being used up. That's a minus. So here we go. Oh, and I just made a mistake. I used the wrong one. I literally just told you, go from where you start. Aluminum oxide. Don't use iron. I just pulled another classic move. It's really easy to make that mistake, as you can see I just did. Be careful. Go from where you started. This is where we started. All right, so I have 2 moles of aluminum and 1 mole of aluminum oxide. All right, so 2 divided by 1 times 2.5 is 5. All righty, because 5 minus 5 is 0. So how many moles of aluminum? I would need 5 moles of aluminum. All right, number 4, last practice example. You may want to pause this video, try it, and then come back and check your work. All right, number 4. Step 1, we have to write a balanced chemical equation. So chromium reacts with chlorine gas to produce chromium 3 chloride. And then we have to balance this. All right, my next step, we go through the mole, but I was provided mass. So step 1, I'm going to have to convert this mass, 255 grams of chromium 3 chloride, into moles, where 1 mole is the mass from the periodic table. And if you do not know how I'm getting this value, you need to go back and watch my video on molar mass. So here we go. This is my moles of product that was produced. That is my after value, because remember, my friends, we don't have any product before a reaction starts. My change is 2 over itself times my 1.61, because 0 plus this value is 1.61. So grams of chromium, here I come over here. I have 2 moles of chromium for every 2 moles of chromium chloride times my change value. Now we're making the assumption that chromium goes and gets completely used up. So what value minus this gives me 0. All right, so 2 divided by 2 times 1.61 is 1.61. So here is my moles of chromium that is required. Now I'm going to have to convert this into grams, where 1 mole of chromium is going to equal the mass of chromium from the periodic table. And so that's going to be 83.7 grams of chromium is going to be required. How much chlorine gas is required? All right, so I have 3 chlorine gases over, where did I start? I started right here. So 3 chlorine gases over my 2 chromium chlorides. My change value is 1.61. Now we are making the assumption that we are using up all of our reactants. So 3 halves times 1.61 is 2.415. And now I'm going to go out a little bit here because rounding causes errors. So I didn't round as much here because I want to round at the end. I'm going to worry about my significant figures at the end, not in the process of. So I'm going to take my moles of chlorine gas, and I am going to convert that into grams of chlorine gas, where 1 mole is the mass of chlorine from the periodic table. And again, when I solve for this, now I'm worried about my significant figures. I'm going to do 3 sig figs there, and I get 1.71 grams of chlorine.